Hello, this is video 74. I'll be talking about Archimedes' principle. It's very closely related to the previous video 73 on buoyant force. So, what is Archimedes' principle? Before we can understand Archimedes' principle, we need to talk about what is displaced fluid. It's best explained by looking at this picture that I have here. When you have your object not in water, your rock is not in water here, it does not displace any fluid. It doesn't push any fluid out of the way. But once you put it into the water, you can see that the level of the water rose because the rock here pushed the water out of the way. By how much did this water level rise? Well, it must have risen by the same volume that the rock took up when it was in the water. So the volume of this rock here must equal the volume of the water that was pushed out of the way. And this is what we call the displaced fluid, is this volume of water here that was pushed out of the way. So that's what I have written here. A completely submerged object always displaces a volume of liquid equal to its own volume. That makes sense. We're going to use the subscript FL to refer to the fluid displaced. So I'm making a very big note of this, right? Using a whole 2 bullets here to explain this. That when you see V sub FL, VFL, it actually stands for the volume of the fluid that was displaced by your object that was submerged in that fluid. The reason I'm making a note of this is because a lot of students, when they see VFL, they think, oh, this means V fluid. This means the volume of the water. But it has nothing to do with V fluid. It has everything to do with how much liquid was pushed out of the way by our object. But we just don't want to write all of those words out. So this is our abbreviation. So just keep that in mind every time you see this FL. Let's take a look at Archimedes' principle. We're ready now. Let's take a look at this picture first. This is also usually a demonstration that I do. I weigh an object in water. We just talked in a previous video on buoyant force that when you put something in water, it appears to weigh less. So this is exactly what this object does here. What happens to it? It weighs, let's say this is in newtons, the scale measuring the weight is 3 newtons. Well, once it's weighed in the water, it now only weighs 1 newton. It appears to weigh this 1 newton. So it appears to weigh 2 newtons less than the original weight. What happens to that 2 newtons? Look and see what happens. The water was full to the top here. When the object was placed into the water, it displaced some fluid, right? It pushed that fluid out of the way, and that fluid was caught here in this second container here. So first of all, what do we know about this amount of fluid that was displaced? It must be the same volume as the object. Now, what do we notice about the weight of this fluid that was displaced? It's 2 newtons. It's exactly equal to the amount of force that was exerted on this block in order to push 2 newtons of water into this container. So I know I just said a lot of words here, but let me just repeat myself. When you place an object in water, it's going to experience a buoyant force. That buoyant force on this object must have been 2 newtons in order to be able to push 2 newtons of water into the second container. So now we're ready for the definition of Archimedes' principle, or the statement of this principle. It says, an immersed body is buoyed up by a force equal to the weight of the fluid it displaces. And this is really a mouthful, and that's why I really like to explain it with this picture here. What Archimedes' principle is saying is that this object that's in the water experiences that buoyant force, B, right? It's buoyed up by force. The buoyant force it experiences is equal to the weight of this fluid right here. This buoyant force must be 2 newtons to equal the weight of this liquid that was displaced by the object. So we can have an equation for Archimedes' principle. The buoyant force is now equal to the weight of the fluid displaced. Remember this definition FL here? The subscript meant fluid displaced. We can rewrite the weight of the fluid displaced in terms of the volume of the fluid displaced. And let me do this because it's very important. We know that weight is equal to mg. So the weight of the fluid displaced, the weight of this liquid right in here, is equal to the mass of the fluid displaced times g. We saw in a previous video that we can write mass as density times volume. This comes from the definition of density, which we said was mass over volume. Just multiply both sides by v, you see that mass is equal to density times volume. So you can see here that if you replace mass by density of the fluid times the volume of the fluid displaced, that's the mass of the fluid displaced. So B, the buoyant force on an object that is placed in water, is always equal to the weight of the fluid displaced, which is equal to rho fluid, V fluid times G. Let's take a look. Let's take a look at one question on this topic. It says, blocks A, B, and C are all the same size. Which experiences the largest buoyant force? So I want you to think about this one. You're definitely going to see this one again. We have 3 blocks. They're all the same size, but they are at different depths, and they also have different masses. Block B is 40 grams, while the other 2 blocks are 50 grams. So which one has the largest buoyant force? You may think, oh, well, these 2, A and C, weigh more, they're going to have more force. But one thing that this problem reminds us is that the buoyant force has nothing to do with the weight of your object. The buoyant force has everything to do with the weight of the liquid that was pushed out of the way by the object, the weight of the fluid displaced. So this comes into play here, the fact that the blocks are all the same size. If these 3 blocks are all the same size, can you see that they're all pushing the same exact amount of water out of the way? They're all displacing the same VFL, the same amount of water. If VFL, the fluid displaced by the 3, is the same because they're all the same size, can you see that in our definition of rho fluid, V fluid, G for the buoyant force, can you see that if they all displace the same amount of water, and that water has the same density here and here, the water doesn't change density. We say water is incompressible. Its density remains basically the same no matter how deep you go. So if the density stays the same, the V fluid stays the same, the G stays the same, can you see that the buoyant force is the same on all 3? So that's the answer. They all have the same buoyant force. But this shows up a lot. So it brings up a couple of very important points, and that is that the buoyant force does not depend on depth. The buoyant force on an object only depends on how much liquid that it's going to push out of the way. So the second point is that if objects are fully submerged in a liquid, and they're the same size, they're always going to experience the same buoyant force.